aperture is defined as maximum acceptance angle to allow and transmit light by an optical fiber. Multimode fibers allow propagation of more than 100 modes through them. The factors deciding the number of modes that can be traveled through multimode fiber are core diameter and numerical aperture. Having large core size and higher value of numerical aperture have many advantages. Light beam can be launched into multimode fiber more easily. Larger numerical aperture and core may have easy splicing. Now, to derive the formula for numerical aperture, first we consider an optical fiber having refractive index core is N1 and refractive index of cladding is N2. This is core and this is cladding. Consider a light is incident on the axis of fiber at an angle θ1. Let the refractive index of this medium is N0. At this point, it suffers refraction, goes towards this side and then reflected. So, here is coming from light. This is refraction and that is reflection. At this point, if we draw a perpendicular, then A, B, C. This is the angle of refraction. Consider it is θ2 and that is angle of reflection phi. Now, using Snell's law, NO sin θ1 equal to N1 sin θ2. From this triangle, in triangle ABC, θ2 plus phi equal to 90 over pi by 2. So, value of θ2 can be pi by 2 minus phi. Putting this value in this equation, we get NO sin θ1 equal to N1 sin pi by 2 minus phi. Sin 90 minus theta is equal to cos theta. Therefore, this becomes N1 cos phi. Now, when this angle is equal to acceptance angle, then total internal reflection phenomena occurs. Therefore, phi is equal to critical angle. In that condition, we can write θ1 approaches to θa, that is acceptance angle, phi becomes phi c critical angle. So, putting these value in this equation, we get NO sin θa equal to N1 sin cos phi c. Now, at this boundary, we use Snell's law again, which means sin phi c equal to N2 upon N1. Then cos theta, cos phi c can be written as 1 minus sin square phi c, and therefore we get sin theta equal to N1 1 minus sin square phi c. Putting value of sin square phi c, we get 1 minus N2 upon N1 square. Solving this, we get under root N1 square minus N2 square upon N1 square. From this can be cancelled out, therefore we get N1 square minus N2 square power 1 by 2. The left hand side of this equation means NO sin theta A is called numerical aperture, written as NA equal to N1 square minus N2 square power 1 by 2. Here N1 represents refractive index of core and N2 represents refractive index of cladding. If we define a relative refractive index difference delta equal to N1 square minus N2 square upon 2N1 square, then from this equation N1 square minus N2 square can be written as 2N1 square delta. So put this value, we get numerical aperture equal to 2N1 square delta power 1 by 2 or N1 2 delta power 1 by 2. This is also formula for numerical aperture in terms of relative refractive index difference. Again, if we consider delta equal to N1 square minus N2 square upon 2N1 square can be written as N1 plus N2 into N1 minus N2 upon 2N1 square. N1 is approximately equal to N2, then delta can be written as N1 plus N2 means 2N1, and this cancel out from numerator, we get N1 minus N2 upon N1. This is relative refractive index difference. For short communication system, the value of numerical aperture should be 0.3 to 0.5, and for long communication system the numerical aperture value should be 0.1 to 0.3.